Live here first. Yep, perfect. Okay, so f of x equals a b to the x. All right, so the last section we were working on polynomial functions. And on polynomial functions, the exponent was a numerical value. Okay, so we had x cubed, x squared, x to the 1, x to the 0, and so on. Now when we're looking at an exponential function, the variable x will be the exponent. So that's going to create a graph for you in which you are substituting in for the a and the b values. The b value is what we call the base value. Okay, so the base value is the numerical value that has the exponent on it. The a value, it's treated the same way as the a value is treated on the polynomial. If a was greater than 0, things open this way. If a was less than 0, things open or changes. It changes the end behavior. It changes the increasing, decreasing part of the function, and it just changes the shape of the graph. That's what a does. Okay, so when we're looking at a typical exponential graph, and actually I'll use this right here, y equals 2 to the power of x. All right, so, okay. Now, one of the things that we have to do is we have to write the characteristics out of this. So this is a typical y equals b to the x graph, in which the base value is 2. Now, when I have an exponent of 0, so 2 to the 0, 3 to the 0, 4 to the 0, 5 to the 0, what does that equal? 1. It equals 1 every time. So anytime you have an exponent of 0, it's equal to 1. So what that means is this, is that no matter what the base value is, these graphs are going to cross at 0 and 1. Because the x value is 0 here is your exponent, so it's 2 to the 0, or 3 to the 0, or 4 to the 0. It'll be at 0 and 1. So that's one of the primary characteristics of this. All right. Looking at this graph right now, I'm going to go through a pile of them to go through this rather quickly. But to look at this graph right now, end behavior is what? 2 to 1. Does not cross that axis. Okay, and I'll explain that in a second. End behavior is 2 to 1. Increasing or decreasing function? What is it? Increasing. Increasing. How do I tell? Slope, sure. Yeah, okay. But what I want you to know, because this was hard to tell in the polynomial section, as x gets larger, what's happening to y? It gets larger. Therefore, it's considered increasing. If x were getting larger and the graph was coming down, that's considered a decreasing function. Okay? Now, there is an asymptote here. Remember what an asymptote is? Asymptote is a line that cannot be crossed. It will be approached, but not crossed. There is an asymptote here. Does anybody know what the equation of that asymptote is? Well done. Slightly off. Nope. She was close at x equals 0. It's not x. Y equals 0. Y equals 0 is a horizontal line. Yeah? So if I were just to put it in, just so you can see this, again, this is an asymptote. So there it is there, right? So that is where y is equal to 0. That graph approaches it but does not hit it. Therefore, if that is the case, how many x-intercepts do I have here? 0. Doesn't touch it. Y-intercepts? 1. Okay? So let's look at and let's write out the characteristics to start with for this guy. Okay, number 1. Y-intercept is 1. That's the first thing that we need to know. Okay. Number 2, the domain. X is an element of all real numbers. Goes left forever, right forever. Number 3, the range. Y is greater than 0. Y is an element of all reals. So Y is greater than 0. Some would say that might be redundant, that we don't have to put the Y as an element of R in, but I suggest you put it in. Okay, it's not necessary, but I would put it in. All right, the 4th characteristic of this is there's an asymptote. At Y equals 0. So those are the 4 characteristics. There is one more, but I can't remember. Oh, so actually what I should do, and I want you to make a note of this too, please. I should write that in there. I do need to show the asymptote on the graph. Okay? I do need to show that asymptote. And I show asymptotes. There's, again, 2 schools of thought on this. One is it should be solid. I think it should be dashed. To me, because it's not an actual line that's on there. It's an imaginary line that implies that the graph approaches it. Now, does everybody have that down? Just up to there. Okay, I just want you to put your pencils down for a second now. Okay, I want you to look at this right here. Pulls that out. I want to go here. I want a table here. Okay. So I have a few values on here, and this is for y equals 2 to the x. Now I want you to think this through for a second here. So the first thing we do is, again, my equation is y equals 2 to the x. So I'm going to substitute x values in and solve for y, okay? All right, so as you can see here, if I start at 0, I put 2 to the 0, that is 1. 2 to the power of 1 is what? 2. 2 to the power of 2 is 2 to the power of 3 is 8. 2 to the power of 4 is 16. So it gets going up real quick. It gets up real quick here, okay? Because that's what happens with an exponential function, is you're multiplying that value, that base value by itself multiple times. Now, let's look at what happens on the opposite side of this. When x is equal to -1, that gives me 2 to the power of -1. What does that equal? Okay, so I just want you to think this through for a second. It's not a minus. Think back to grade 10 and 11. A long time ago. When I have a negative fraction, a negative exponent, how do I make that exponent positive?
1 through 2 high. 1 through 2 high.
Yes. Okay, very good. Okay. What we decided is we did this. We took it and we moved it to the bottom and changed the exponent to a positive. 1 over 2 to the power of 1. Well, what is 1 over 2 to the power of 1? It's a half. Now let's start looking at it in terms of this. What does that equal? 1/4. What is it? 1/8. Okay? 1 over 2 squared. 1 over 2 cubed. 1 over 2 to the 4th, 16. So what's happening as my negatives keep going to the left on the x? What's happening to the y value? What is it? You said it. Decreasing. You said it, getting smaller. So it's getting infinitely smaller, yes? I went from a half to a quarter to an 8 to a 16 to a 32nd to a 64th to 128. Getting smaller, 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 smaller. But cannot reach 0. Cannot reach 0. All right, so it's going to get closer and closer to 0. So therefore, that is why I consider this an asymptote right here. because these values, the further I get out here, the closer it's going to get it to the x-axis, but it's not going to hit it. All right? This is exponential functions. All right. Now, the next thing I want you to do on this part of it is, all right, what happens? What does this mean for us? So when the a value, the value in front of the base and the exponent is greater than 0, all of these occur. Y-intercept is 1. Domain, x is an element of all reals. Range, y is greater than 0. Asymptote at y equals 0. And behavior, let's put that in here because we're in grade 12 now. Let's put that in here. Let's add that. 2 to 1. Okay. I'm missing one other one. I can't think of it. No x-intercepts. Okay. Now, here's the catch to all of this. All right. If a is less than 0, if I put a negative in here, what do you think then happens to the graph? Excellent word. Over what? X-axis. I like that. What do you think happens here if that a is less than 0? I think it flips it down here. Why? What is the other shape that you have dealt with for 2 years now that it flipped over? Yeah, what is it? The quadratic. What happened when a was less than 0? It flipped and opened down. Yes? Okay, perfect. Okay, so let's have a quick look. Let's add the negative into here. Et voila. That whole graph goes that way. Now, perfect. Now, we've got one other thing that we have to be concerned with, and that is this. What happens if, okay, first of all base values have to be greater than 0. So let's get that straight first. All base values, the b, has to be greater than 0. If they are greater than 1, all of these characteristics occur. What happens though if that base value is a fraction? What happens if that base value is a half? How does that change the graph? If my base value y equals 1/2 x, how does that change that graph? What do you think happens here? Maybe decreasing instead of increasing. Okay, there's one, possibly. Anybody else?
The exponent is negative because
Yeah. Yeah, that's exactly what she said too. Yeah. Okay, so what's going to happen here? Well, let's start at x equaling 0. If x is 0, what is y? 1. If x is 1, what is y? 1/2. If x is 2, what is y? 1/4. If x is 3, what is y? 1/8. If x is 4, what is y? So as x gets larger, what's happening to the value of y? It's decreasing. Exactly what Ella said. It now becomes decreasing. So that graph is then going to have a bit of a different shape to it. So we're going to go here. I'm going to delete that. I'm going to go 1 divide. Put that a 2 down there. Put that here. Over there. And that's it there. All right. So let's take those out of there. Put this out of here. Put this, and there you have it. Okay. What is the end behavior of that graph? Still 2 to 1. That doesn't change. What's the y-intercept of that graph? 1. How many x-intercepts on that graph? 0. What's the equation of the asymptote? Y equals 0. So none of that changed. The only thing that changed was it went from an increasing to a decreasing graph now by making the base value a fraction. Right? So remember, b has to be greater than 0. The base value has to be greater than 0.
So x equals 0 would be the vertical one that doesn't touch the line. Or like would that not happen?
If we were to shift it, if it's shifted, that is a possibility. Yes. But we, I'll show you the logarithms right away. And everything is inverse. Then x equals 0 is actually the asymptote for that. Okay. So let's rip through some of these. Okay. Let's rip through a few different equations now and see how everything gets adjusted. All right. Graph each, you're going to fill this in on the practice question there. So fill in your blanks in your book. Page 179, question 1A. The equation is y equals 5 times 2 exponent x. All right, so here's what I have here. Okay, first things first. Question says, how many x-intercepts are there? 0. What is the y-intercept for this graph? 0 and 5. 5 is the y-intercept. But I just said over here that the y-intercept is 1. But that is if the a value is 1. If the a value is anything but 1, the a value is the y-intercept. Okay? And that's because the first thing you do here is go b to the 0 and then times it by whatever the a is.
So if it's anything but 1, it's the y.
That's right. Okay. End behavior. What's the end behavior? 2 to 1. Domain. X is an element of all reals. Range. Y is greater than 0. Can it be equal to? No. Okay. Easy peasy. Let's do this one. What is it? 4 times, is it a quarter?
Yeah.
There you go. Okay. Y-intercept. Oh, I went too quick. There are how many x-intercepts? 0. What's the y-intercept? 0 and 4. Good. End behavior? 2 to 1. Can somebody? I don't believe everybody knows what end behavior is. Is there anybody in here that doesn't understand end behavior? Nathan can't be the only one. Is there anybody else?
Put your hand up. Oh, it's simple.
Okay.
Explain it.
Nathan, whatever quadrant it starts in on the left of the graph, so the arrowhead would be up here.
Yep.
That's in this quadrant here. That's 2.
Okay.
That's where it starts. Where it ends is which quadrant does the right arrowhead end in. In this case, it stays in this quadrant, so the end behavior is 2 to 1. It's where it goes from left to right. Okay? That's end behavior. All right. Domain, x an element of all reals, and the range, y is greater than 0. Okay. Look at page 180. Okay. Page 180. Number of x-intercepts is 0. What's the y-intercept? What is it? 0 and 8. The end behavior? Still 2 to the 1. Domain? X and element of all reals. Range? Y is greater than 0. Whether this function is increasing or decreasing. This function is decreasing. As x gets larger, y gets smaller. There you have it. That's all I need to do. Flip to 7.3 now. Okay. Seven point three. Modeling, which means regression. So the last section we did linear, quadratic, cubic regression graphs. We're now going to do exponential and then logarithmic today. Okay, so exponential graph. Just start with this. You guys can just follow me on the board here. 1951, what is it? 1951 and 776.5. What's the next year? 1961, and that is?
921.
Good. 1971, I'm guessing. And
998.9.
1981. 1035.5. Thank you. 1991.
1109.
2001.
1151.4. And 2011. 4258.6.
Thank you. Okay, so I'm right there. Again, regression graphs. So I got my table. What do I do next? What do I do?
Hit the line button so that it makes the graph.
Okay, well, I'm going to hit the zoom button just to see where these points are. Right here. That's the first thing I'm going to do. That didn't work. Do it again. There we go. There's my zoom button. Okay? So far, we understand? Now, what do I have to do to get the regression part of this? Sorry?
It's a line.
Right there. Again. There we go. And which regression are we talking about? Exponential. There you have it. Okay. Now, gonna move it way over. Okay. So it gives us the equation of the exponential function. The a value is 0.00149854. The b value is 1.006806 to the exponent x. That's it. Construct a scatter plot to display the graph. Use exponential regression to define a function that models it. When it says use exponential regression to define a function, that means write the equation there. So that B part is saying write the equation down. Assume the same growth rate. Estimate the population in 2020. Okay. So I need to find when x equals 2020. And right there. Population will be 1336.14. Then it says estimate when the population is 1,500,000. So when the population is 1,500 according to our graph. So I go down here. Y equals 1,500. Here and there. 2037. So I put in x equals for the second graph. I put y equals for the third graph. All the information is there before me now. It's pretty simple. And again, the reason it's so simple is you're using Desmos for this. This was not set up for Desmos because it's way too easy. Yes, ma'am.
So sometimes in the book, they would use the equation.
Okay, we had this conversation yesterday.
I'm just making sure you don't want to
I don't want you to do it. I want you to use Desmos to get your answer. Stop chatting. Okay? So finding intersection points using Desmos. Okay, are we okay with exponential? Because I'm about to shoot you to logarithmic, which is another function. All right? And then from there, okay, so looking at this graph right here, logarithmic is the inverse of this graph. I don't know if we've talked about this yet. To find the inverse of any graph, you take all x, y coordinates and you make them yx. That means you switch the x and the y values. Now, graphically speaking, it's a reflection over the y equals x line. So if you were to fold this, if you were to take this right here as a sheet of paper, you would fold it over like this. This graph would look like that. That would be a mirror image of it. That is the inverse of that graph. The equation for that particular graph.
Excuse me, Braden Tanaka to the office, please. Braden Tanaka.
Is that. The equation for that graph is y equals a log x to the base b. Now there's a lot more that can go into this, but all I need for you is to understand the graph of this. When we get to pre-calculus, I'll go into the other stuff that works with this. Now, the question always is, well, what's the point? Well, what the logarithm allows us to do is change any base value to a base value of 10, which is what we count in. So that's what it allows us to do. Graphically speaking, if I am to graph this guy, this graph looks like this. All right, in which that coordinate is 1 and 0. Now think about what I said to start this little spiel off here. What was the y-intercept for the exponential graph? The y-intercept was 0 and 1. Well, if I take the inverse of that coordinate, I switch the x with the y. What does that then become? 1 and 0. So that is my new value. So now what I'm going to do is I'm going to write this out yet again for logarithmic. Number 1, x-intercept, 1 and 0. Number 2, the domain for this graph. Anybody want to have a go at it? Thank you very much. The domain for this graph is x is greater than 0. Range? Equation of the asymptote. X equals 0. Okay. End behavior. Nathan.
Huh?
Tough one for you here, bud.
Oh, God.
Okay, we talked about end behavior. So looking at that line right there, the green line, Nathan, that little arc, which quadrant does the left side of that arc start in? Two. Okay. You probably don't know your quadrants, do you?
They left and right, like 1, 2.
1, 2, 3,
Oh,
4.
ah, fuck. 4 to 1.
Attaboy. End behavior for this graph is 4 to 1. End behavior is 4 to 1. Okay? How many y-intercepts are in this graph? None. None. Okay, that's what we need to know about logarithm so far. All right, it says predict the x-intercept, the number of y-intercepts, and the end behavior, the domain, and the range of the function y equals 14 log x. So to graph it on Desmos, I go y equals 14. I have to go to functions here to find it. I think actually you can type it in though. I believe you can type in the word log. Let me make sure. Come on. There it is there. Log x bracket. And then, why is that not? Give me the opportunity to. Okay, there it is there. Okay. Now, I need you to look closely at the equation itself. This is something different than that you're not used to, but the equation I just put into here is y equals 14 log x like this. The base value hasn't been identified in it. The base value for this is 10. If there's no little number subscript written in there for a base value, the base value is 10. Okay? So that's like saying, and now how to read this. That's the other thing. There's so much we got to go through, but how I read this is this. That is the log of x to the base 10. That's the function. It's a function. Log is a function. It's like an operation. I try to relate it to like the trig. Sine, cos, and tan are functions. So they convert using ratios and stuff. Logarithm uses base values and numbers to convert. All right. This would be said to be the log of x to the base 2 because my base value is always this. Now, what you will learn as we go through this is if I take the log of x to the base 2 and I let it equal to y, like that. All right? I can change this into an exponential function by taking the base, moving it up to the right side. This becomes the exponent, and it works like this. Those two things mean exactly the same thing. The log of x to the base 2, if it's equal to y, then x is equal to 2 to the exponent y. Now, this is called the change of base formula, but we don't need it just yet. We will, but not yet. Okay. I think everything's good. And then I don't think I need to go through the regression graph with you for that one. But if you have a regression graph, again, use your table. Put your tables on there. Table, put it in, and then do your logarithmic graph. Okay? So there is a lot there to cover over the next couple days, but you have a half an hour right now to take your Desmos out, use it on your own right now, and fill in the blanks in your book to get the questions done as quickly as you can. All right? And I will let you know. So Friday for sure, you have the assignment. I'll let you know through Friday where you need to be for Monday. And then Tuesday, I suspect we should be wrapping this whole thing up, this chapter 7. Okay? And then we might just have one assessment day so that we can get chapter 8 done before Christmas, if that's possible. And we may not get it entirely finished, but we may get it. We should be pretty close.
Is chapter 8 really hard?
It's on trig graphs. No. Okay. Any concerns today? All right.
So you're not